Alright, let's look at some of those sequences and series questions that you got and we're working on in class over the last couple of days. This will help prepare you for the test on sequences and series, which also covers compound interest and exponential equations, but this first 11 questions will focus just on the arithmetic and geometric sequences and series. So let's start with number 1. We'll calculate the sum of the first 30 multiples of 4. Now we haven't been told yet whether this is an arithmetic or a geometric sequence, so why don't we write out the first few multiples of 4 to see what we observe. Okay, so the first few multiples of 4 are 4, 8, 12, 16, etc. Now, it's pretty clear that the differences between each pair of terms are equal to one another. And because these differences are all equal to one another, we say that there's a common difference, and so therefore that must mean that it's an arithmetic sequence. And I'm going to make this identification right at the beginning so that I can remember to use the arithmetic formulas for the rest of this question. So it says to calculate the sum of the first 30 multiples. So the first 30 multiples, that means there's 30 terms. We're looking for the sum of the first 30 terms. So let's substitute into the arithmetic sum formula. So we've got 30 over 2. 2 times the first term, which is 4, plus 30 minus 1, that's the n minus 1, times the common difference, which we can see is also 4. And if we put this into the calculator, 30 divided by 2 times 2 times 4 plus 29 times 4. We get an answer of 1,860. Question number 2. Let's calculate the number of items in each of these sequences. What we've been given, the number of terms it says. So because we've been given the final term in the sequence, that's known as un. So let's use the un formula. We know that un is equal to u1 times the common ratio to the power of n minus 1. So what is the common ratio in this situation? Alright, well let's see. We've got to check to see whether it's an I guess I already knew it was a geometric sequence, but perhaps I could have tested that first. I could have looked at the common differences. 3 over 2 minus 1, that equals 1/2. But 9 over 4 minus the term in front of it is equal to something different. We get 3 over 4. So because these are different values, it cannot be arithmetic. Let's just check to see if it's geometric. 3 over 2 divided by the term in front, that equals 3 over 2, or 1.5, your calculator will tell you. And we've got 9 over 4 divided by the term in front, 3 over 2. That also gives you 1.5. So this is a geometric situation. Just circle that so we remember that we're using geometric formulas the rest of the time. So we've been given the nth term, so our un must be equal to u1 times r, which we now know is 1.5, to the power of n minus 1. Let's put this into the calculator because that's a difficult equation to solve. And so we'll say y1 equals 729 over 64. And for y2, we'll make it the right-hand side. That's 1 times 1.5 to the power of x minus 1. And I can see that my n, the number of terms, must be an integer, so let's use the table method. Second graph to get into the table, and I'm looking to see where are these values equal to one another. If I scroll down a little bit, I'll see that I get them equal on row 7, is where y1 and y2 are equal to one another. So to show the work, I should just probably explain, hey, my y1 I put in as 729 over 64, and my y2 I put in as 1 times 1.5 to the x minus 1. And now I can write a table which includes only the row where I wasn't quite enough and the row where I finally was enough. So row 6, I had 11.391, but I was only at 7.5938. It was when I finally got to row 7 that my values, that's the decimal value of 729 over 64, and my y2 value are finally equal. Therefore, because x is equal to 7, that means that n is equal to 7, or I can say I've got 7 terms in the sequence. Part B, look, I don't have room for it now, but it's obviously the same question. It turns out that it's also a geometric sequence, except that instead of the common ratio being 1.5, you'll find that we're multiplying by 10 each time, and that means that your common ratio is going to be 10, and your first term is 2. And you'll end up discovering, I believe, that your value of n is 12, so the answer to part B should be 12. I can see that, by the way, because this final term right here, I can see as u1 times r to the power of n minus 1. So my 2 is my u1, my 10 is my r, and if n minus 1 is equal to 11, that must mean that n is 12, so 12 minus 1 is equal to 11. And so that's another way that you could find the answer to part B is 12 terms. Let's go on to number 3. The first 3 terms of a geometric sequence are 2, x, and 18. It is known that the common ratio is a positive number. Okay, so then let's write down the ratios of each pair of terms. So we know that x divided by 2, just realizing that I'm going to keep going. X over 2 is equal to the next pair, 18 over x, and I could immediately figure out what x is equal to. So I have to have x squared cross multiply. I've got x squared equals 36. That means that x is equal to 6. So if your x is equal to 6, what is your common ratio? I can see that 6 over 2 equals 3, and 18 over 6 equals 3, so the common ratio would be 3. So I actually already answered this down here. R equals 3, the second term x equals 6, and the 10th term, because it's a geometric sequence, let's circle that to make sure that we use only the geometric formula. It asks for the 10th term, so I'll use the term formula. U10 is going to equal U1 multiplied by R to the power of 10 minus 1. So I'll just type that in. 2 times 3 to the power of 10 minus 1 is 9. Oops, I should have quit this screen first. There we go. 2 times 3 to the power of 9 gives you a pretty big number, 39,366. Alright, but let's go back to part A, because I actually didn't solve it. So all I did was find out what the common ratio, what the x was, so I could figure out the common ratio was 3. But let's actually write down an equation involving the first term, the common ratio r, and the third term. The third term we know is u3. So what do I know about the third term of a geometric sequence? So it's equal to u1 times r squared. So let's substitute the things that I know. I know that u1 is equal to 2, and that r is equal to 3. And so there's your equation. Any one of u3 equals this, or u3 equals this, if you want to have already done the substitution, would be okay. I'm guessing that most of you hadn't already solved for the r, and so you ended up finding it was just u1, it was your 2. So 2r squared was all that you were able to write, and yes, that would also be acceptable for full credit. Okay, let's look at number 4. I remember in class this tripped up a lot of you, so let's just break this down one more time. This is like saying 2 plus negative 1 plus 0.5 plus negative 0.25 plus etc, etc, etc. So the things that we're adding together, some of them are positive numbers, and some of the things that we're adding are negative numbers. I guess we could write that as positives and negatives with pluses and minuses instead, like addition and subtraction, but you can also write it as a sum of positive or negative values. Alright, let's look for whether it's an arithmetic sequence or a geometric sequence. So let's see, negative 1 minus the term in front gives me negative 3. 0.5 minus the term in front, negative 1, is equal to 1.5. These are not the same, therefore it is not an arithmetic sequence. Let's try geometric. Negative 1 divided by the term in front gives you negative 0.5. 0.5 divided by the term in front also gives you negative 0.5. These are equal, so it is a geometric sequence, and I'm just going to write that down for myself so that I use only geometric formulas for the rest of this question. Now at this stage I can see only that u1 is equal to 2, and I've also established that r is equal to negative 0.5. But if I want to use the sum of these terms, I need to know not only u1 and r, I need to know the value of n. How many terms are there in the sequence? Well, back in number 2, we did a bit of practice like this. We had a look at the last term, and we know that the last term is the same thing as un, or if you like, it's u1 times r to the power of n minus 1. So a couple of ways we can do this. The quick way would be that you got lucky because this is already written in nice exponential format. We can see that u1 is 2. R is equal to negative a half, or negative 0.5. So that must mean then that n minus 1 is equal to 25. So if n minus 1 equals 25, you'll quickly discover that n is 26, and you're going to have all of the information that you require to find the sum of these first 26 terms. But some of you might not have looked at the last term and realized that it fit the form of u sub n so perfectly. No problem. Let's actually substitute it into the un formula. We know that un is equal to u1 times r to the n minus 1. Your un is being given to you as 2 times negative 1/2 to the power of 25. You know that your first term is 2, that your r, we said, was negative 0.5 to the power of, well, let's make it an x minus 1, so now we can use the calculator. So we can look to see when are these two values equal to one another. I'm a little worried that they're going to be such small numbers, maybe they won't even show up on the table. So we might end up having to go back to our solution where we recognize that these two expressions are basically the same coefficient, the same number as the base of the power. So 25 must equal x minus 1, which brings you back down to x or n equals 26 anyway. But I'm just going to try this on the calculator. I'm kind of curious. So maybe our first expression could be 2 times negative 0.5 raised to the power of 25. And the second expression is 2 times negative 0.5 to the power of x minus 1. And, trying to figure out what's happening here. Got some weird stuff at the end. Oh, I've got the x minus 1 twice, so let me just delete those. Okay. Hope that works out. Looks okay. So again, because I know that x is going to be an integer, because it represents the number of terms, then let's look at the table. And if I look at the table of values and scroll down far enough, so you can see that y1 is always equal to this weird thing, negative 6e negative 8. If I keep going far enough, come on. There it is. I can see that on row 26, that's when my y1 expression and my y2 expression, both of them represent negative 6 times 10 to the power of negative 8, which means that both of them are incredibly small numbers close to 0. But we can see that they're equal in the 26th row, so n equals 26. So that substitutes into the sum formula. Sum of the first 26 terms, we've got 2 times negative 1/2 to the power of 26 minus 1, all over negative 1/2 minus 1. We'll put this into the calculator. So we got then 2 times, open brackets, negative 0.5 raised to the power of 26, and then I'm subtracting 1, close the brackets, and let's divide by the entire denominator of negative 0.5 minus 1. Minus 1. Hit enter, and it tells us the answer is 1.33333333, which you can just round to 1.33, at least, right? But no less than 3 significant figures. Okay, we'll continue this in the next video.